deep learning? No, no deep learning.
Yes, yes, yes. An introduction to deep learning, but in very general, like, and even I used your video, and we went over some of the a notebook. Maybe we could like show it on this screen. Let me see. I wasn't ready for that. Sorry.
Is- Excuse me, Luis Fernando, because I'm a little bit lost because I was thinking today we were going to talk about deep learning
No,
and deep learning.
this is the second session, Professor. So this was like, so we have already.
Ah,
So
okay, 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 okay. So the first session was like an introduction to deep learning, right?
yes, and we even started with some of the information about some of the basic introduction to how to 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 perform some embeddings, on to get information from the graphs, to pass it to a machine learning algorithm. Like a node-wise representation first, and then I guess we stop there. If you want, let me just. I'm going to try to recover here
Okay, so that we know where to start. Okay.
okay, yes, yes. Let me just
Be-
show that. Just so
okay. And did you review Keras?
not in detail actually. We just went over we went over one notebook. That's what we did, but not in a lot of detail. Let me just maybe go over here. I guess here. This is it. So let me just maybe. Sorry about that.
Okay.
Of the class, and we gave it an
I, but
to.
Profe Luis Fernando, I think that was all what we did last time. Oh, sorry. I was thinking that this was the recording
No,
from
this
that
was
last session.
yeah.
This is the recording from 2 weeks
Last
ago.
Yes, yes, exactly. It's because I used some of the material that you already have in the video, and then maybe
Oh,
also gave some
okay.
at the beginning about this basics on artificial intelligence, machine learning.
Oh, but
Sorry,
I think there is not more material to cover today because
no,
I think that was the
the
last
spectral
thing we
thing.
did.
The spectral thing. Remember the spectral thing? But maybe I think we can recap on this because I think this was a little bit fast about how
Okay.
this
Okay. And
paper.
then
These are
and what about the notebook, the next notebook?
No, I did. I just showed one notebook, the first one. So I think we could continue with the second notebook.
Okay, so we can continue with the second notebook. Okay.
Exactly.
And we can recap here because that's all what we did last time, no? Like, 1 year ago,
Yes.
right?
In general, the concepts were basically those ones, and maybe recap on this, about these embeddings or these mathematical transformations, or how you convert, let's say, the graph into a vector representation that captures the essential information of the graph. And then maybe I think maybe we can spend, because this was a little bit fast, talk about
Yeah.
convolutional neural networks, because I think that was very fast, and maybe not all of them are familiar with this type of neural network. We just gave the
Okay.
general
Okay.
idea, but I think we can still go deeper on this concept.
Okay. Sorry, when you sent me the video, I didn't get that. Yeah, that it was from the last session that I was thinking that was the material I was supposed to cover today. Okay, perfect. Okay.
Sorry about that with the students. The misunderstanding between us. Sorry about that, but I think we are good.
Oh,
We're good still.
yeah, we can start here from this. Okay, good. Okay. So two things I would like to discuss. Maybe continue from from the last class, the discussion about deep learning, because deep learning is like a very hot topic nowadays. And actually the current models are really powerful. Things like transformers and large language models, all that is happening. So also we can discuss a little bit about that. And but yeah, let's continue with what you were doing last time, and then we can't open to questions and things like that. Okay, okay. So
Yeah, Professor,
let's.
maybe as you mentioned, sorry about that. One thing I think maybe talk about convolutional neural networks and in general deep learning, regarding deep learning, what is underneath, that these transformations that occurs automatically, like what we call feature extraction methods that
Mhm.
actually networks do it. And in the case of these neural networks that are specialized in text natural language processing or text processing, the how they this transformation occur there in that case for when it comes to text.
Okay, okay, good, good, excellent. So yeah, so let's continue with this, and then we can discuss about the other topics. Okay, okay. So quickly to recap. So yeah, the idea here in general is how to use neural networks, and in particular deep neural networks, to solve different type of tasks on graphs, where the input is a graph. Okay, so that's interesting because it is not obvious, and I think actually the work on the graph neural networks came later, after work on images, work on tests. That was like the first kind of successful deep learning models. The first one were models basically working on images, and then tests, and more recently on graphs, because this is not obvious. Okay, so yeah, so a deep neural network is basically what which is shown here is basically a succession of layers connected in different ways. Okay, something which is very important is that a graph has different levels where we can work on, which is very particular again. Like when you are working with images or you are working with tests, the structure is very clear and is given, and in the case of an image, is the structure of the pixels that are organized in a kind of grid. The test is a sequence, but a graph, the structure is richer, and actually kind of problems that you can solve uh, art. There is a combination of things that you can do at the level of the vertex or nodes, at the level of edges, or at the whole level of the graph. Okay, okay. So, and again, you can have information at the level of the vertex, at the level of the edge, or information about the whole graph. In fact, many of the things that you have discussed in the course, the different metric or measures that you can calculate in a graph, like for instance, centrality measures, etc., are in fact features that you calculate at the level of the graph. But then the fact that you have these different levels, global level, edge level, vertex level, makes this kind of a structure uh, definitely richer in terms of the information that you may have, but also challenging. Yeah, because how do you codify that information to give that information to a network? Okay, okay. What else do we have here? Yeah, for instance, yeah, the fact that a typical information that you can give to a neural network, for instance, images, you can think of that information as a graph. So actually, the graph representation is really a very flexible way to represent information. You can represent different kinds of information. The thing is that representing, for instance, an image as a graph may be very costly, right? So the way that typically an image is processed in a neural network is using something which is called convolutions. I don't remember if later here we have convolutions, something about convolutions, and actually, let me see. Yeah, because this is long, right? Okay, but yeah, but I don't remember, Prof. Fernando. Do you remember you, because I saw in the video something that you were showing about convolutions? I don't remember it was in this presentation or it was somewhere
Yes,
else.
yes, yes, yes. It was here at the end, somewhere later in this paper.
No, no. Yeah.
Or someone
No,
some
no, it's a link. It's a link
oh,
here.
it's a link
Yeah, yeah.
somewhere. Yes.
Yes, but yeah, we will go there. Yeah, yeah, here. Uh, okay. Okay, yeah, let me continue a little bit to discuss about this. Um, yeah, and we can go to that. So actually, the way to deal with this in neural networks with images is use a particular structure that exploits the regularities. Because see, this is a graph, but this is a very regular graph. You see that the pattern of connectivity of the graph is homogeneous around in most of the vertices or the nodes. You see the pattern of connectivity is the same basically. Okay, so that's something that you can exploit in a neural network. The problem is that in general, in a particular graph, on an arbitrary graph, you don't have this homogeneity. Okay, so actually, something which is very interesting is how to apply those same ideas of that works very well in images like convolutional neural network, how to apply that to graphs. So yeah, we will discuss a little bit more about that. Okay, so yeah, a test, you also can see think of test as a graph. Another kind of data that's what you have been reviewing through this course. Okay, okay, good. Okay, social networks, etc. Okay, okay. Here there are some examples of typical data sets that are used both in network science and in the deep graph neural networks with different numbers of graphs, or for instance, in this data set, which is a data set of molecules, you have in the order of 100,000 graphs. And then there are other data sets like these other ones here where you have only one graph, but the graph is huge with hundreds of dozens or millions of nodes and millions of edges. Okay, so there is a great variability on the kind of data you can deal with. Something which is very important is that when you are dealing with these scales, definitely this is big data. This is large amounts of data, and that's the kind of scenarios where deep learning can provide very interesting results, because deep learning is very hungry on data. So when you have large amounts of data, that's something that you definitely can exploit. Okay. Okay. Okay, so there are tasks at different levels. So at the ground level tasks, for instance, here, which is a classification of molecules, depending, for instance, in this particular case, where the molecule has two rings or not, things like that. Tasks at the level of a node. This is the classical karate club problem, where you have a small social network, and then you have some nodes which are aligned with one person, another nodes, other persons which are aligned with another leader there. So that's a task at the level of node. What I have to classify here are nodes, whether they are from one side or the other. And then a task at the level of the edges. Typically, for instance, you start with a fully connected graph, and then you have to assign some class to the edges, or even you may cut or eliminate some of those edges, okay, and only leave those edges which are interesting for the interpretation of the data. For instance, in here you have like a kind of a scene, and then you have objects on the scene, and then you want to know what's the relationship between the different objects in that scene. So that's an example of a task at the level of an edge. Okay. Okay, so yeah, the problem with using graphs in as input for a neural network, and in general in machine learning, is the flexibility of the structure. Okay, so see that, and let me go. I think this is a good time to go to talk about convolutions, because I think this illustrate well the problem. Okay. Yeah, I think this is a good illustration of the challenges of dealing with graph information in neural networks. So, for instance, if I have a feature vector such as this, let's say this is, for instance, information of a client that has to do with his salary, the age, the income, the credit status, etc., etc. And I want to classify the client as a good client or bad client to give a credit. So a lot of information has this structure, that where the samples are structured as records. Okay, so this is very easy. So if you have a vector as input to a neural network, is very easy, because to design a neural network, because the neural network is basically neural network with as many entries as the fields in the record, in the input record. Okay. So that's easy. But if you have a graph, how do you codify the graph to give it to the neural network? That's the question. Okay. That's the question. So that's not easy to answer. That's not easy to answer. Okay. So, yeah, for instance, here you have two molecules, and then this molecule has a lot of atoms, and how do you call that, bonds. This is a smaller one. Okay, and then those are like two samples that you will input to your neural network, and this has more information, this has less information. How do you deal with that, with the fact that the structure is not homogeneous? So that's a problem. Okay. Okay. Yeah, the order of the nodes is important. Okay, so it's not the same. See that this is the same graph here, but the labels of the nodes are different. Okay, so here you have A, B, C, D, etc., and here you have A, B, C, D. Okay, and then if you calculate the adjacency matrix, for instance, of these two graphs, the adjacent is the same graph, but the order of the rows and the columns in the adjacent graph is going to be different because of the different labels on the different order of the labels, and then those are going to be two matrices representing the same graph but which are totally different. Okay. Okay, the other problem definitely is a scalability. Okay, the amount of data you may have in a graph may be huge. Okay. Okay, so let me I'm not going to go into details here, but yeah, but I just want to discuss this idea because I think it's interesting, so that you can see the difference that you may have in data that behaves very well, like images, and data that behaves very bad, like graphs. Okay, so that you can see the challenge. Okay, so let me see here if there is something that illustrates a convolution, because this is talking about convolutions on graphs. Yeah, this is getting very technic. Hmm. No. So let me tell you what happens. Yeah, probably I have this in this presentation. Hold on a second. Yeah, I have this. So I will share this to show to tell you how images are deal with in typical neural networks. Okay. One moment. Let me share this. Yeah. Yeah. Here. Okay. Share window. Okay, so in convolutional neural networks, basically, okay, so this is the motivation. By the way, that's an old idea. The people that propose that we can organize neural networks as using the inspiration on the way that the visual cortex of our brain works. That was proposed by these guys, Fukushima, in the 80s. So it's very old idea. The problem with the convolutional neural networks is that it's difficult to train. So actually, the first practical neural networks to solve problems appeared like 15 years ago or something like that. Okay, so but the idea is solved. Okay, so basically the idea is this in a convolutional neural network is if you have an image, for instance, like this one, and you are designing a neural network, uh, typically you use a multi-layer perceptron. Basically what you do is for each uh, input or for each, in this case, the input is the image, but the image is composed of pixels. So in this particular case, for each pixel in your image, you will have like a connection to each one of the neurons in the first layer of your neural network. So imagine that this image is 100 by 100 pixels. Okay, so that means that you will have 10,000 pixels. Okay, so you will have 10,000 connections here for this neuron, and then for the second neuron, you will have 10,000 connections, and so on. So you have a layer here on neurons, let's say 100 neurons, and then for each neuron, you have 10,000 connections. You will have 1 million connections between the input and the first layer. And it's a small image, 100 by 100, and is a small layer, only 100 neurons. Okay, so that's very big. So the first idea is, okay, don't connect the neurons in this layer to all the pixels in the input, but to small regions. For instance, here this neuron connects, let's say, to a region of 4 by 4, is only to 16 uh, pixels, this neuron to 16 pixels, this neuron to 16 pixels, and so on. So if you had 100 neurons here, but each neuron connected to only a small region of 16 pixels, you will have 100 times 16, which is 1600 1600 connections, okay, 1600 connection, which is a small number of connection compared with 1 million. Okay, so that's the first idea. The neurons only connect to a small area in the input. Okay, okay. How is that done? Okay, there is a second idea. The second idea is that the weights of these neurons that connects to the input are shared. So the values of the weights of this neuron are the same as the values of the weights of these neurons, and so on. What's the motivation of that? For instance, imagine that you are training a neural network that is able to detect cats. If a cat is in some part of the image. So really it doesn't matter if the cat is here or here or here or here. Really you want your neural network to be able to detect the cat wherever it is. Okay, so basically what you do is you are doing this assumption that the neurons share the weights, is like codifying something which is called the translation invariance. Okay, so that the patterns that your neural network is able to detect doesn't depend on the position. Okay, so if you do a translation, it doesn't matter, your network continues to work. That's called a translation invariance. Okay, that's implemented with something which are called convolutions. A convolution is basically something like this. You can think of this is a concept known in the uh, signal processing. So you apply something which is called a filter, and then you do a convolution of your filter with the signal. The signal is the image, but basically what you do is you these are like a matrix of weights. You multiply these weights by the values of your input matrix, and you move this small matrix of weights, which is called a filter or a kernel. You move that in your image, and this is going to generate, when you do the multiplication of each element by each element in this portion, and sum those elements, this is going to give you a value, and then when you move that, this is going to generate like a kind of image or an output image. Okay, so that's which called a convolution. You can see an animation there of how the convolution works. Okay, and the result of making a convolution is like a small version of your image with multiplied by those values in the filter that here are represented by like red numbers that you may see there. Okay, so you may have many convolutions. Okay, applied to the input image, and then you may have many layers of convolutions applied. For instance, here, you may have many layers. So here, for instance, I apply convolution, but each one of these, you can see that they are like images which are stuck there. And then each one of these is like a different convolution with different weights. And then you can apply another convolution. Well, okay, here you do something which is convolution and subsampling, which is another operation which is called pooling. And but you can do that several times. Okay, so basically what you do is you transform your input image like in several images that represent different features of your data. Okay, but the important thing here is the fact that you can do that because your image is homogeneous. Okay, so let me see if I have something else here to show. Okay, this is pooling, which is like reducing the dimension. Let me go back to the mm, where is it? Here? Yes. So that's something that you can do because the connectivity of the pixels is homogeneous. Okay. The thing is that, for instance, here in this one, basically what the yeah. Mhm. Okay. Uh, Let me see if there is something more intuitive here. Yeah, this an example of what we were discussing. The applied a convolution to okay to a input image. Okay. Okay, but the challenge is how do you apply that to a graph? Okay, how do you apply that to a graph? And this is what which is in this page that I suggest you to give an idea is basically they extend the idea of convolution to graphs, so which is very interesting. Okay, the problem with the yeah, probably this is better explained here. The problem with uh, uh, um, graphs is that they don't have the homogeneity that you have in images. So here, where is the image where we have that example here? So this is the graph corresponding to an image, and then you see that the pattern of connectivity is the same for independently of the pixel. In a graph, you don't have that. But the nice idea of graph convolutional neural networks is that you can extend the idea of a convolution to something which is not homogeneous like a graph. Okay, so that's something very interesting that you can deal with. Okay, so just to give you an idea of the contrast that we have with typical data like images and then using graphs. Okay, so but there are ways to deal with that. We are not going to discuss graph convolutional neural networks, but that's something which is very interesting, a very interesting topic. Okay, this is another challenge. Okay, and I mentioned it just when we were in the other page. This is exactly the same graph? Okay, this is the adjacency matrix for. I think this is a play, and this is the interaction of the different characters in the play. But if you reorder the character, which are the nodes, like here, you get two matrices which are totally different. Okay, that's a problem because actually something that you may think that you can do with applying, like trying to apply convolutions to graphs is I can build the adjacency matrix and then apply the convolution like the one that we discussed. The problem is that the same graph may have as many combinations or permutation of the nodes, so that's a problem. Okay, so that doesn't work. Okay, these actually are all these are for, see, this is a very, this is the same graph, but basically all these are adjacency matrices of the same graph with different permutations of the nodes. Okay, so see, is this is crazy. Finding a pattern here is impossible. So the naive idea of applying a convolution to the adjacency matrix doesn't work. Okay, okay, okay. So yeah, these are different ways to represent a graph. Okay. And yeah, so here you have the nodes, here you have the edges, okay, and then you have the adjacency list, okay. Okay, so that's a typical representation, but which is clear is that you cannot fit this representation directly to a neural network, so you have to think of different strategies, okay. Okay, so basically, you have different ways to deal with this. Okay, so hold on a second. Okay, let me see if we can explain this. Let me see.
Meanwhile, Professor, I just shared a very nice interactive link. I mean, where you can like visualize the effect of what happens in convolutional neural networks. So just for the students to,
Ah, okay, an interactive node link visualization convolutional neural. Ah, oh, okay, thank you very much.
that's a very nice link actually, where you can visualize what happens in the
Okay,
different
okay.
in 2D and 3D, by the way.
Okay, okay, thank you. Yeah, that's a good resource to understand what happened with convolutional neural networks. However, the point here is convolutional neural networks are very elegant, very nice, because images are, you think of images as graphs, they are very homogeneous. Okay, so everything works very nice there. Okay, everything works very nice there. Okay, okay. So the thing uh, with graphs is that we have to think of different alternatives to deal with the different kind of information that we have, okay, in the graph. Okay, so the idea is basically that in a graph neural network, yeah, no, I was thinking that there was something that was clearer, but I hope that I can explain it in a simple way. The idea is this: basically, what you do in a graph neural network is that you transform the information that you may have in the edges, sorry, in vertices, edges, or the global information. Okay, so you have information. You have transformation at the level of edges, vertices, or global information. Okay, so in each layer you can think of as an outdated version of your graph. Okay, so here you have the graph in time t or layer sorry, time n or layer n, and this is the transformed graph in layer n plus 1. Okay, okay. So to illustrate that, let's see some simple examples. Okay, So see that you can do transformations at the level of edges, vertices, or global. So let's see, for instance, the kind of information that you can do at the level of vertices. Okay, so this is only considering vertices. Okay, so here basically you have a um, okay, no, but let me see here. Let me see. Yeah. Okay. Sorry. Yeah. So here, basically, what we have is the nodes. See that the nodes could could have been transformed at the by sources by different layers. So here, basically, what you have is like the last layer where you take each node and then you perform a prediction. Okay, so basically, you can think of making a prediction as this kind of transformation that we were thinking about. Okay, so at the level of node, for instance, you take the information inside each node and then you say, okay, I will assign a class 0, 0, 0, and then class 1 to this one. Okay, so think that the final classification also can be seen as a kind of transformation in the graph. Okay, okay, so uh, for instance, yeah, this is an example. The thing can be complicated, okay? Yeah, because here I go from nodes to nodes. From each node, I take the information and then I make the classification. So that's simple. But there are cases where, for instance, you don't have information in the nodes, you only have information in the edges, okay? You don't have information in the nodes, you only have information in the edges, but you want to get information in the nodes because you want to classify the nodes. Okay, you want to classify the nodes. Okay, so imagine that, for instance, this is a kind of a social network where you don't have information of the individuals, but you have information about the social relationships between the individuals. For instance, the messages that they interchange, the topics of the messages that they interchange, but the individuals are anonymous, okay? But you want to make like a feature vector for each individual in your social network. Okay, so you have information in the edges. Okay, in each edge you have information. Okay, and then how do you build the information for a particular node? For instance, for this node, you take into account all the edges that how do you say the edges which start or end in this node. This is an undirected graph, all the edges related to this node, and then you sum the representation of those edges to build a representation for the node. Okay, so saying here, for instance, this is only connected with this and this, with these two. So this is you add those two to get this representation, and this is represented with two. Then you add that to build this information, and so on. Okay, so the transformation is not only from node to node, but you can also transform information that goes from the edges to the node, from the node to the edges. Okay, to illustrate this one, basically, yeah, you have something that goes from the edges to the nodes. Okay, so this, which is illustrated here, that we are like transforming the information on my graph using information of the edges and moving that information to the nodes. Okay, okay. So for instance, this is another example. You only have information at the level of the nodes, and then you want to do some, then you don't have like a feature for the edges, and then you want to classify edges. Let's see, for instance, suppose that these are like some biological compounds, and you have information of each biological compound, and then you want to predict if two compounds interact in some way. There are like two types of interaction, or not interaction at all, or some type of interaction, which can be positive or negative. You have information of the compounds, but you don't have information on the edges. But the task that you have to solve is a task of classifying the edges. So you take information from the nodes, and then you integrate that information in the information of the edges, and then you apply that classification to get a final classification of the edges. Okay, so see that this is like the general framework. Okay, you have global information for the nodes, information for the edges, and then you can apply different transformation of that information, taking information from node to edges, from node to nodes, from edges to node, from edges to global, etc., etc. Okay, so here what this is illustrating are all those kind of transformation that we can apply. Okay, okay. For instance, this is I do some transformation on the graph that takes information from the vertices and integrate that as a global information to do a global prediction. Okay, okay, okay. So that's basically the idea. You start with a node, with an initial node, sorry, with an initial graph, and then your neural network transforms the graph neural network in each layer in a new graph that can move information around. Okay, that's the idea. That's the idea. So you start with a graph, and then after several transformations, you finish with a transformed graph, and then you apply classification, and the classification could be at the level of the nodes, at the level of the edges, or at the level of the graph. Okay, I hope that was clear. Okay. Okay, so you can do that in different ways. Let's see what's this illustrating. Okay, so yeah, this is a typical one. For instance, this is taking information from nodes to nodes. So, for instance, this is see, just to illustrate what's going on here. These are like feature vector for each node here. Okay, so all these are feature vector for each node. Okay, so for instance, if this is a social network, this is information for different persons. Okay, like socio demographic information, or interest information, etc., etc. Okay, so the transformation is basically what you do here is in the next layer where you are transforming your graph is integrate the information of the neighbors of a node. For instance, in this case, the neighbors of a node are or this node are these. I don't want to choose. Are this and this. Okay, so the information is here, plus the information of the original node. So you sum all that information, you integrate all that information, and then you modify the representation of this particular node. Okay, so basically this information here is the integration of the neighboring nodes. Okay, see that this follows a principle that says that's not a principle. It's like that's something that has been studied that says that in some way you start to behave and to look like the people that you are around, or your friends. Okay, so basically what this is doing is that modifying the representation of each node, integrating the information of the neighboring nodes. Okay, so for instance, for this one, it integrates the information of those three nodes, itself and the other two. And this, for instance, integrates information of all the five nodes because it's connected with all of them. This integrates the information of three nodes, itself and the other two, and so on. Okay, so that's an example of the type of transformation that you may perform. Okay. Okay. What else do we have here? Uh, yeah, there are several combinations. See, for instance, this one here. You go from node information to transform edges information, and then you integrate the edge information to again calculate node information. You go from vertex to edge and coming back from edges to vertex. Okay. Okay. And different combinations here. It illustrates. Yeah. So see that definitely there are many things that you can do with a graph. It's very rich. Here, for instance, you got back and forth from edges to vertices. Okay. Okay. And then you have global representation. See all these interactions. Okay. So yeah, this could get as complex as you want. What we are going to do next is to check a particular example. In particular, what we are going to do, I think, is something like this. At the level of the node, we are going to do something like this. Okay, integrating information at the level of the node. Okay, we will see. Okay. Let me see here what we have in the graph neural network playground. Okay. So, okay. Okay. So basically what we have here is a problem of classifying molecules. Okay. So the molecules are basically there are two classes, pungent, which I don't remember the translation, or not. So this is a problem of classifying the molecules according to the odor. Okay, this is called the Leftingwell odor data set. Okay, okay. So there are only two labels, uh, and uh, and that's something which is a problem which is interesting in chemistry. And each molecule, as you may suspect, is represented as a graph. Okay. And basically you have these kind of atoms or elements: carbon, nitrogen, oxygen, and fluorine. And then you have bonds between those which are represented as edges. Okay, so our problem is to classify, making a global classification of the molecule. Okay, then this is using a graph neural network. Okay, that with a number of layers. Um, mm, so and here they describe what they do. Let me see if there is a graph of the. No, let's read the description. Here they said uh, they do basically this. Node edges and global representation are outdated with the information of the using what is called mesa spacing, which is this what we discussed here, what we saw here, basically here. Yeah, actually, yeah, I didn't say that, but here when you are basically outdating the representation of a node based on the neighbors, okay, here you are using the information of the neighbors, you can think of as the nodes passing to this node to update the representation. That's why this is called mesa spacing. Okay, so basically what they are doing here is that. Okay. Uh, yeah. So basically, what you that you may have like a baseline model, because at the beginning you have information for the different the different nodes, okay, the different nodes in the graph. But then with the layers here, you can specify the number of layers. uh, 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 you update the information of the graph, your representation of the graph, and depending on the number of layers and depending of the function that you use for aggregation and depending on the representation that you use for each node, you may get a more or a better, a richer representation of your graph that may be solving the problem easier. Okay, so something that you can do is very simple, is you can just have don't do all that mesa spacing thing, and then you integrate the information of the graph at the end, and then you make a classification. Okay, but here the interesting thing is that the graph neural network is transforming the graph in different ways. Okay, just to understand here what's going on. So it has three layers. You can specify the number of layers. Okay. So here a layer is something that behaves like this. Sorry, let me go here. Something that behaves like this. So this is going like the one layer. So a layer basically, if you have three layers, you will do this three times. If you have four layers, you will do this four times. There is something which is called embedding. We will go back to that, but to 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 don't go back and forth. The embedding size is how do you represent the information in a node. Here, the embedding size in this example is 1, 2, 3, 4, 5, 6, 7, 8. That means that we are representing each node by 8 values. Okay, so see that to update the representation of this node, we add the embedding of itself, which is this, plus the embedding of this one, plus the embedding of this that one, and we sum them. But we can calculate the average, we can calculate the maths. There are different ways to do that. So, there are different things that we can change. So the number of layers, so how many times we apply this? The embedding size is the size of the vector that represents each node, and then the how we aggregate the information. Here we are summing. So let's go back here. Okay, so three layers. We are aggregating user sum, but we can use the mean or we can use the maths. The embedding size, here we are using 50. We have an embedding also for the edges, okay, which is 10, and an embedding also for the global, which is 50. Okay, okay. So let's play with it to see what happened. Oh, this is already trained. Okay, so we change this, or whenever we change something, yeah, this is the accuracy. This what you see here is a representation. This is using dimensionality reduction of all the data sets. So each point here is a molecule. So if I point here, this is a molecule. Okay, okay, and then the red ones are yeah. Let me see here the red ones. Yeah, are positive, which is pungent, and the green one are negative, non-pungent. But you see that you have around is you have the inside and the outside. So the inside is the model prediction, and the outside is the ground truth. So, for instance, this one is something where that the model says that is red, that means pungent, and is actually pungent. So this is well classified. And let's see one which is not well classified. For instance, this one. Okay, this is classified as grown through is pungent, but the model says that it's not pungent. Okay, but 81% of the molecules are well classified. We can play with, for instance, let's make it the simpler one. Only one layer, only 25 dimensions for the node embedding, 5 dimensions from the edge embedding, and 25 dimensions for the global embedding. Okay, so yeah, you get 69. And let's get the most complex one. Not necessarily is the one that works the best, but let's see. No, actually, you have to look for a good combination. Not necessarily, you see. Let's put here 50, 10, 50. Okay. Yeah. And then use match or use mean. Okay. 81%. That's what we have at the beginning. Okay. So this illustrates the kind of things that you do in a graph neural network. Okay. Basically, what you do is you transform in each layer of your neural network. Basically, what you do is you transform your graph, modifying the representation of edges, nodes, or vertices, and the representation of the global graph. Okay. Okay. I hope this has been clear because actually it's kind of tricky. But yeah, I will open it to see if you have questions, if you have suggestions or comments. Any question till here? Everything clear? So may I ask you? Well, okay, let me do a quick quiz. Okay, oral quiz. Okay, let me see here. Okay,
Quick
Random.
question
Juan David,
regarding the. Mhm.
sure, tell me.
Eh, So when we were seeing the convolutional transformations and all of this, we see that that we get a model. Let's say when we have this image, I remember that it was like a chicken, and after the transformation, we get the same chicken, but with in low resolution, right?
Mm-hmm.
We have a transformation similar to that one, let's say, but in graph, let's say to have this.
Yeah, that's good question. That's very good question. So in convolutions, you can think of something analogous to this. Analogous, but really you are not encoding information about edges. You are not encoding information about global information of the image. You are only encoding information about the pixels, which are like the nodes or vertices. Okay, so when you something that you can do in an image is you can like reduce the resolution of the image, and you do that with an operation which is called pooling. Okay, so with pooling, and typically you do that. You do convolution, convolution, pooling, convolution, convolution, pooling, something like that. Okay, so and actually, when you apply convolutions, depending on the parameters of the convolution, you can also reduce the resolution of the image. So that's something that you can do in images because of the way that the information is represented there, and because they are very homogeneous. Here, really, the the graph doesn't change. It's like you have always the same resolution for an image. Okay, from a layer to layer, the graph, you keep the same structure of the graph. What changes is the information that you have in the vertices, the edges, or the global information of the graph. Okay, so that's a difference. Definitely, it's a difference. You don't transform for instance, you don't reduce the number of vertices, you don't reduce the number of edges, you keep it same from beginning to end. Okay? So that's a difference. Any other question? Manuel,
Thank
Alejandro.
you, teacher. I have a question, and is when we aggregate the information between different vertices, what happens when one node has missing information? What can do? What can we do in that case?
For instance, here, let me see. Here in the example, here, right?
Yes, teacher.
So here, for instance, for this one, basically what we are doing is we are adding the information of see that all of them have the same dimensionality, right? So what we are doing here is we are adding the information that is in this node with the information that comes from the other two nodes, okay? So basically you are aggregating that information, summing or doing an average or doing a match. When you say different, I don't understand exactly what you mean by that.
Okay, teacher. I guess that, for example, one of those beans could be, for example, the age of one of the beans or something
Ah,
like that.
right. Something like that, right? Okay,
Exactly.
but no, but there is something. Yeah, you are right. You are right. Actually, typically, what happens is that this information is initially it could be some characteristics like that what you mentioned, but those characteristics are transformed. Okay, I mean, typically what you do is something which is called an embedding. Okay, so initially you may take the characteristics of the node, and then you calculate some vector that represent, but you learn that vector that represent the node. Okay, and that's called an embedding. So typically these embeddings here are not associated with particular characteristics of the node, but those are characteristics which are learned by the neural network. This is like a representation which is learned from the data. I don't know if that's clear.
Okay, teacher.
For
But
instance,
okay.
imagine. Let's say we have images. Each node is an image, and the images are connected in some way. Okay. So yeah, let's say what you have here are images, okay, and the images are connected according to some criteria. I don't know, okay, and that's your graph. So something that you can do is, and typically you do is from the image you can calculate an embedding. An embedding is you can take, for instance, a convolutional neural network. That neural network receives the image and gives you a vector of some dimension, okay. So that's like your internal representation of the node, which is an image. So here you don't have the image, but you have like an internal representation of that image, which is an embedding. And then when you train your model, you train everything, the convolutional neural network for the images and the graph neural network and all that. Okay. So this is a learned representation. Okay. We will see that in the example that come next. Okay.
Okay, thank you, teacher.
Okay. Okay. So any other question? Okay, let me see here. Okay. To see, let me see if this is clear. Okay, so I will ask somebody. Uh, let me see. Paula Jimena Rodriguez. Paula Jimena, you can open your mic. And you can you can't answer in English or Spanish. Don't worry. Paula, we don't hear you. I don't know. You have permission to open your mic. Let me see. I think I don't can change that.
No, I think they all have they are
Okay.
able to open the mic. I don't know if she has some problem with the mic. The mic. Paula,
Paula.
Paula, she has a problem with her mic. Is
Ah,
that
okay. She has a problem. Okay, so you can write in the chat. So, can you explain what's going on here in this image? Or anybody that can help Paula to explain what's going on in this image. It doesn't have to be like the right answer. It's just to
Ready.
Freddy.
It looks like in the final layer we combine the vertex and global information.
Right.
We use
So
a pooling
yes,
function.
yes, exactly that. So first thing that Freddy says is we combine information. So we combine the information of vertices to the global information. Okay. So see that here at the level of vertex, I have information as many information vectors as nodes I have. Okay. So combining that information, that's what they call pooling. So how do you, what kind of operation can you do to do pooling here? For instance, Freddy. What,
Well, I
what
think
could,
that
yeah,
about ponderate a weighted sum of the vectors, maybe.
for instance, yeah, a sum of the vectors, okay? A sum of the vectors. Something that could happen, see that here, the representation of the at the level of the node is not necessarily okay here yeah just it was the same but here for instance the representation at the level of the node may not be the same dimension as the global information, okay, but it doesn't matter. Actually what you can do is typically what happens is yeah let me go back to the where is it, the one that we were discussing. Let me see. For instance, there we had, yeah, here. For instance, we have dimension 25, but the global information is 50 or something like that. So typically what you do is you apply the transformation that goes from 25 to 50. So you put in the same dimension as the global information. And then you do some pooling, okay, to aggregate information, as Freddy was mentioning, some, ponderate some, or something like that. And then you get information for only one vector representing the whole graph. Okay, and then after you get that vector, what do you do, Freddy?
Sorry, teacher, can you repeat me, please?
Yeah, then you were saying you take the information from each vector, then you aggregate that information. That's the pooling. And then you have only one vector representing the whole graph. And then what you do with that vector?
The classification.
For instance, yeah, for instance,
You make a prediction about
you make a prediction. Okay, you make a prediction. Exactly. That's it. That's it. You make a prediction, and that's it. That's is, basically that. Okay. And a prediction means, for instance, yeah, a neural network that receives as many inputs as the representation of the whole graph, and has an as output, for instance, only one neuron that could be 0 or 1, or a value which is 0, close to 1, to solve a binary classification problem. Okay, so yeah, that's an example of the kind of things that you may do. Okay, thank you, Freddy. Okay, what happened, Paola? We were waiting for you for his explanation in the chat, or you agree with Freddy? Okay, okay. I suppose so. Okay, so I think we can go to the question. So we had this. Probably we can go quickly to this one. Uh, eh, Profe Fernando, did you review in detail this notebook last time? Or?
Yes, but I guess we didn't go all the way to the end. I don't know. Maybe you can. Yeah, we went over some of the details about the classification problem there.
No, then what I'm going to do, yeah. So what I'm going to do is I'm quickly go over it, just to remind, because I know that these are a lot of information, and after 1 week you may forget. So a quick recap, okay? If you agree, okay? So first of all, we are using Keras, okay? Anybody can tell me alternatives to Keras nowadays? If I don't use Keras, what can I use? In the chat, could be. What alternatives to Keras? Oh, Keras is a framework to training neural networks. So what else can you use? PyTorch, right? That's like the competition. TensorFlow, and actually, that's something interesting, because here we are using Keras with TensorFlow, and at that time, by the way, let me see. Yeah, let me. I will open this in playground mode so I don't. Yeah, and let's run it. And yeah, at the time this was I created this notebook. Keras and TensorFlow. Keras was integrated in TensorFlow. By nowadays, Keras is not anymore. I mean, before Keras was not part of TensorFlow, then it was integrated, and now again is a something which is separate. Okay, so Keras and TensorFlow are separate. Okay, so really the two main alternatives. Okay, no, really there are more alternatives, but nowadays the two dominant frameworks for neural networks are TensorFlow and PyTorch. Okay, PyTorch is created by Meta, and TensorFlow is created by Google. Okay. There is another framework which is popular nowadays, which is called Jazz. you write it, yeah, this one. No, that's Google. Ah, yeah, this one. Yeah, this is Jats. This is created by by Google. Um, Really, you can use any one of these to solve these kind of problems, but it depends. So typically, TensorFlow is kind of easier to use. Typically, with Keras. Okay, but what's Keras? Keras is actually a meta framework. So if you go to the documentation of Keras, you will find this. Yeah. Yeah, this is not TensorFlow anymore, and they say that they support JATS, TensorFlow, and PyTorch. Okay, so actually, Keras is like a meta framework. It's something that you can use in conjunction with PyTorch, with TensorFlow, and with JAS. Okay, and basically, what Keras makes is like it's easier to specify models that using directly TensorFlow or PyTorch. However, typically Keras has been associated with TensorFlow traditional, and PyTorch. No many people use PyTorch with or Keras with PyTorch. Okay, so typically you use Keras. Probably you are going to use TensorFlow, but probably that's going to change with the new version of Keras. And if you use PyTorch, you either use directly PyTorch or something which is called Lightning, which is like the Keras for PyTorch. So which one to use? It depends. TensorFlow with Keras typically is easier, and there is a lot of documentation to learn. But PyTorch could be more flexible and powerful. So it happens that a lot of research nowadays, I will say more, probably most of them, is done in PyTorch. So if you will go and look for a code from a paper or something like that, it's very likely that you will find it in PyTorch. Okay. Uh, but for practical applications like industry applications, things like that, TensorFlow is more popular. Okay, so my suggestion is if you really want to get into deep learning, you have to learn both TensorFlow and PyTorch, but they are very similar, and Keras probably is going to make that easier. Okay, okay, so why runtime disconnected? Okay, okay, so let's see if this is working.
Professor, I don't know if we, since this may take a while, if we make have to take a break and then we can go over the whole thing after the break.
Yeah, that's perfect. So, what time are we ending the class today?
It's gonna be at 9 p.m. But
Okay, okay, no, but probably it's going to be shorter. So yeah, this is a good time to make a break, and then we can come
yeah,
back
and
and
if you don't, if you can maybe give us a few minutes because we are planning the last session. The next session is just to present the project.
okay,
The final reports of the project, the class project. But maybe we can spend a few minutes to talk a little bit about the some frontiers of the network science. And we can even we have the video from last time, and I think we can maybe
good,
highlight those things if you wish.
excellent, excellent.
Okay.
Yeah, yeah, I think good idea. So, how long the break?
10 minutes.
10 minutes,
Ten
perfect.
minutes. Okay,
Let's
so
do it.
it's
Okay,
actually like 7:30, so it's 7:40 we'll be back.
okay, perfect, excellent.
Okay.
Okay.
So see you guys in 10 minutes. Okay, I guess we can continue, Professor. Is everybody
Thank
back?
you. Thank you, Professor Fernando. Okay. Yeah, I think we can go directly to since you already reviewed the Keras notebook, and I think we can quickly check some of I mean, we can use directly the node classification with graph neural networks notebook, okay? All the students have access to this material, right?
Yes, but we can we share the link to the collab note,
Of course.
please, to the notebook, for
Yeah,
that notebook?
I will put it here so everybody can make his own copy. My suggestion is to save to your drive so that you can go and play alone. Okay, okay. So first, we are going to use here some. Well, okay. Let's start with the baseline model. I think you reviewed some part of this baseline model, right? Last time.
Excuse
Professor
me?
Fernando.
What?
You review the first part of this notebook, right? Last time?
The no, no, I think the node classification notebook.
No. This is
I
the
think that we can
acceptation network, right? No.
you can go over the whole thing. I think is better.
Okay. Let's do it. Let's do it. Let's do it. Okay. No, I'm not sharing my screen. Sorry. I'll share it right away. Okay. Okay, so yeah, you have the link. Yeah, thank you for. Okay, see, and remember, anytime you can raise your hand or write in the chat or open your mic if you have any question. Okay, okay, okay. So here we are going to work with a data set of scientific publications. So those are papers. That data set is called Cora. Okay. You can find it here. The links of the data set are here. And actually, we can go there just to take a look. Okay, so this is the data set. The good thing of this is papers with code. Here you can see different benchmarks for this data set. Uh, um, Let me see, the numbers are here. I don't see. Oh, because these are different tasks, not classification. Let me see. Uh, yeah, and this is how they have evolved through the time. And the best right now is something that get like 90% of accuracy. Let's see how much we are going to get. Okay, today. Okay, so the data set is composed of 2,700 scientific publications, and each publication is belongs to one of seven classes. Okay, the interesting thing is that this is a citation network, so you have which paper cites or refers to which paper, okay? And then there are around 5,000 links, citations between the papers, okay? So the problem is to classify the papers, okay? Um, for each paper, we have some information. The information is basically a one-hot representation of the test of the paper. I don't know if the test comes from the abstract or comes from the full document. I don't have it here. Let me check quickly. Let me check here quickly what they say. No, they don't say it either, but probably it's from the abstract, okay? And there is a vocabulary of 1,433 words. So for each paper, uh, they check if a particular word appears in the paper, and they will put a one in that vector of 100, digo, 1,400 positions, and they will put a one in the position corresponding to the word, and zero in those words that don't appear in the paper. Okay, so you have for each paper this description, the feature vector of 1,400, and then you have the links between the papers. Okay, and the problem is to predict the class of a paper from the 7 classes based on that information. Okay, okay. So here we are. Yeah, let me open in playground. Okay, and let's run it alone. Okay. So here we are getting the file. Wow, I have to import. Okay, here is downloading the data. So this is what we have, the Cora sites and the Cora content. So this is the information about the citation. So all the links of the graph, and this is the information of the vector representing the content of each paper. Okay. So okay, and there is a README here that I print, etc. These are the classes, by the way. Those are machine learning papers. So case-based, genetic algorithms, neural network, probabilistic method, reinforcement learning, rule learning theory, etc. Okay, okay. And then here we are loading the data. So this is the information of the citation. Here you can take a look. This is the way it looks. So you have the okay. This is a sequential number. There are 5,429 links, and this is the target, and this is the source. So that means that paper 6,771 cites the paper 1999. Okay. And that's it. And see that the numbers are not necessarily consecutive numbers, so we have to deal with that. We will see. Those are like IDs of the papers. Okay, so source, target. Okay. Then here are the information of the papers. So you have 2,708 paper, and each paper is described by a vector of 1,435 positions. Okay, okay, and then here is the basically information. Okay, so you have the paper ID, the terms for each paper, and yeah, a lot of zeros. Okay, there because yeah, for a particular paper, you here actually this is only one paper. Okay, so this is only one paper. No, these are 5 papers, but each paper is in a column. So the paper with this ID, these are all the terms that appear in the. But yeah, this is just a sample. Okay. And this is the subject of that paper. This is genetic algorithms, this is neural network, this is neural network, this is case-based, okay? And this is theory. And see that there is no a one on this small sample, okay? Okay. Then here we can count the number of samples per class. So we have 818 papers on neural networks, 426 in probabilistic methods, and so on. Okay, that is, I will say, the balanced data set. Okay, then we have to do some processing to convert the IDs to consecutive numbers. And yeah, that's done here. Okay. And then we can visualize the graph. This is, we use network edge that you already know to doing the visualization of the graph. And let me see. Okay. And here you have, this is the network. Okay. So there is a, like, some core or paper that has a lot of citations between them, and then there are some outsider papers around. Okay, okay, okay. So we are going to do a train test split. Okay, of the papers. So we are going to divide the papers in train and test. Okay, so basically what we get here is 1,000. Let me see. Here we print the train data shape and the test data shape. Okay, so we get 1,333 papers for training, 1,375 for testing, and each paper is represented by the vector, is the same size for all the papers. Okay, so first we're going to build a baseline model. Our baseline model is a neural network. Actually, it's a neural network that is, we will see it. And yeah, let's take a look to the network. The network is this one. Yeah, but I had to run all this. Yeah, but let me show the, yeah, there is a graphical representation of the neural network. And we can go over the code. So this is our neural network. So it's a neural network that receives vectors of 1433, the size 1433, and then it goes through different layers, okay, of 32 neurons, okay. Mm. Uh, the only interesting thing is that this has something which are called skip connections. This kind of connections, the purpose of the skip connections is, Daniel, go ahead.
Thank you, Professor Fabio. Do
Yes.
you know if the number of nodes in this case, but the number of the parameters in the first layer can be changed?
Oh, yeah, of course.
One
I mean,
hand.
oh, you mean, okay. There are two things. One thing is the size of the representation. The size of the representation of our data, which is, I mean, for each paper, for each node, is
Yes.
1435. That's it. That's the way that the data set is organized. But
Yes.
inside our neural network, we can define the layers. For instance, here we are specifying that the hidden units are 32, but actually, basically, what we do is we have like blocks of, for instance, let's change this. Let's say this is 3264. Okay. So what happened there? Let me create again the neural network. And then, yeah, we can change that. Okay. So
Okay.
what was that 32? You're not using the 32. Hmm. Hmm. Why? Okay, I changed the 3264, and I don't see the 32 anyway here. Well, okay, we will check. But yeah, we can change that. Okay, the internal structure of our neural network, we can change for sure.
Thank you,
Okay,
Professor.
okay. So, yeah, this is a multi-layer neural network, nothing strange here. The only thing which is particular, this is taken from the example, the pages where I took, where, yeah, I took this from two places and organized this notebook, is that it uses something which are skip connections. Just to tell you the idea of skip connections is because this is a neural network with, yeah, you can see many layers here. Okay, but the skip connection, basically what they do is they make the training of the neural network faster because gradients can flow in a faster way through the neural networks. Okay, so these skip connections are just to make this to train faster. Okay, and see, so several layers with those skip connections, and then you have at the end an output of 7 neurons that corresponds to the 7 classes. Okay, so this is our neural network. Okay. Yeah, so nothing strange here. So our baseline model is a model that receives a paper represented by this vector, okay, or the 1433, and outputs the class. But see that this doesn't use the citations, okay? It doesn't use the structure of the graph. It's taking each node independently. That's why this is our baseline model, okay? Okay, so yeah, and here is the code to build that. Just quickly to take a look to the code. There is a function to create the small blocks of a, yeah. Why this? Hmm. Okay. Anyway, this is creating blocks of dense layers. Okay, using things like batch normalization, dropout, which are like typical operations that are used in neural networks nowadays. Those operations are used for doing something which is called regularization, which is to keep control of the model, of the complexity of the model. But really the important thing here is that those are dense layers which are densely connected with the next layer, with the previous layer. Sorry. Okay, and then it uses sequential. If you remember, that's like the easier way to assemble things in Keras, putting one layer after another layer. That's it. And then here is like the code to create the baseline model. This is a little bit more tricky, but it's at the end, it's a Keras model, okay? And the model is the one that you are seeing here. The number of parameters of this model is 60, yeah, 68,000 parameters, which are trainable, and 72,000 which are not trainable. Which are those non-trainable parameters? I'm not sure. I'm not sure. What are those non-trainable parameters? I don't know. But anyway, yeah, that's our. No. There are 300, 3,000. But I will have to check. But anyway, it's a model which is not that big. Okay, it's moderately. The size is moderate. Okay, 68,000 is not that big. And anyway, it's our baseline model. So I don't know how long does it take to run. Let's see. Anyway, we don't have to run it full. Let me check if we have. Oh, we don't have GPU. Yeah, let me change the. Yeah, yeah. For this, we have to use GPU if we want to train it. Yeah, the thing with deep learning is that definitely you want to you really need hardware that is able to run uh, these kind of models because of the size of the model, because of the size of the data. Okay. However, the good news is that nowadays it's cheap to have access to this kind of hardware. Okay, either because you buy a card and you put in your computer, or because you use this kind of services like Colab. Colab has like a free tier, so for the small things you can use, but when you run many models using GPU, you are going to like exhaust the free credits that you have, and then in that case you will need to pay, but it's not very costly. You can pay like 40,000 pesos, something around that per month, and then you have a good number of hours to use GPUs if you need. Okay, so let's see how this goes. This is 300 epochs. Okay, so yeah, I think this is going to take a while. No, actually, no that much. Okay, okay, so it's training. These are the curves for the previous while that ends. These are the curves for from the previous run. So basically here what we are plotting, which is typically when you do deep learning, you typically this is the number of iterations, which are called epochs, and then you plot the loss. The loss is like the function that you are minimizing. So for the training data set, and the loss for the test data set. You see here, there is like an inflection point around this epoch. So typically what you do is you save this model. I don't know if the code here is saving that model. Let me see. Let's plot this. Yeah, so here there is like an inflection point here in this epoch. And here, but yeah, the performance intent, yeah, here is the loss and this is the accuracy. Typically, the loss that you use in classification is something which is called binary cross entropy. That works very well, but a way which is better to measure the performance of your model in a more interpretable way is this using accuracy. And here we are reaching like an accuracy around 70% in our validation set. See that the accuracy in the trained data set is bigger, actually goes like to 90%. The thing is that really we are interested on the validation accuracy, because really what we want to see is how well our model works with samples that the model did not see during the training. Okay, so that's why we look at this accuracy invalidation. Okay, so let's evaluate it. Yeah, the previous time we have 74%. Let's see now. 74%. So remember that there was like a 90% there. So this is not bad, but 74%, that means accuracy, remember, is the percentage of samples, in this case papers, that were classified. So 74% papers that are were well classified. Okay, so that's our baseline model. It's a model that ignores the structure of the graph, of the citation graph. Eh, Now we are going to use a convolutional graph neural network. For that, we are going to use a spectral. So what's a spectral? A spectral is this library. It's a library for TensorFlow that allows you to do a graph neural net, train, define and train and test graph neural networks. Okay, so these are examples of the models that they have implemented. Graph convolutional network, Chebyshev convolution. So there are many things in the literature. Okay, diffusional convolutions. Well, okay, there are many things there. Okay, and the good thing um, of the spectral is that it deals very well with graph data. We will see that that's something that what I think is the most interesting part, and I think is the hardest part in dealing with graph neural networks. How do you deal with the data, which is very particular. Okay, so in addition to full models, they have layers that you can use, and yeah, it's very flexible and easy to use, etc. Okay, so let's go to the example, but here you can find tutorials and you can, oh yeah, yeah. So yeah, you can use yeah, there are many resources here and very good documentation. So let's go to the example. Okay. So okay. So you have to install a Spectral. You do it with this instruction with pimp install a Spectral. Okay. And then uh the first thing is we need to create a spectral data set. Okay, so that's something that you have to spend some time doing, but it's very important because it's where you put your graph information. Okay, so there is a class which is called data set. Okay, and then there are other classes, for instance the class graph. Okay, and all that is part of a spectral. Okay, okay. Okay, so basically what we have here is a code that creates that data set. So the data set is a class. That class has a constructor and a method that is called read, and is the one that generate the graph whenever is called. Okay, basically what it does, Daniela, go ahead.
Thank you, Professor Fabio. In the line 11, mm, do you know if I can change the number? I guess that 7
Oh
uh,
yeah.
is the number of words that
No,
is classified,
no, no, it's the number of classes.
the number of
Remember
classes.
that, yeah, remember that the task here is to classify um, the papers according
Yes.
to 7 classes, which are topics of machine learning papers. Okay,
I-
so that's why we have 7 there.
if you increase the value because you have more, it's probably that the model uh, tends or mm, goes to be mm, mm, loss precision.
No,
Actually, that's
actually, no. Actually, you are going to have problems because your data set has exactly 7 classes. Okay, so your data set, yeah, the classes are these ones. Okay, these
Yes,
are the classes of your
if
data.
I
So
have
you
more
have
class.
if you had more classes, you don't have training data for, let's say you put 8 classes, okay? But you don't have a class 8 here. You only have 7 classes. You only have samples for 7 classes. So you have 8 classes. That 8 class is not going to do anything because you don't have samples for that class. So whenever you train your model always is going to predict classes from 1 to 7. Okay.
Okay, what I mean is if I change the data set and it
Oh, of
is
course.
the same model, but my data set use or have more classes, it's probably that the model lost precision.
Okay. what happens? What happens? Because you say you change the data set. So change the data set could means two things. One thing is there is a new data set that has more classes. Uh, so that means that you will need to train your model again. So you will have to train change your model. So that's one thing. Okay, so if you have less or more precision, it depends on the new data set because it's different data. So it could be easier, it could be more difficult. Okay, the other
Yes.
possibility is we train a data set with this, and then we had papers, new papers, a new data set, also old papers, but where you had more classes. The problem is that you are not going to be able to use this model trained with this data set with 7 classes. With you can apply that model to a new data set with different number of classes. Okay, I don't know if that's clear. I think your question is more like a more fundamental questions about machine learning and how machine learning works.
Probably, yes.
Yes, yeah. But see, yeah, just let me make a comment about that. Okay, because yeah, your question is an important question because it happens that for instance, humans we are permanently trained. Okay, for instance,
Yes.
imagine a kid. Okay, and then the kid is a small, yeah, it's a small kid, and then he learns about dogs and cats. He's able to distinguish dogs and cats. But then sometimes we take that kid to the country, and he sees or she sees a horse, right?
Yes.
And then that's a new class, right?
Right.
So what happens with the kid? The kid is going to say, that's a dog, okay? And then we will tell, no, that's a horse, okay? And then what happens is that the kid updates her model to include a new class, okay? The class horse, okay? And that's something which is very natural for us. And it's not like I will have to give to the kid like 100 samples of horses just with one sample. And the next time that she or he is going to see a new horse, probably is going to say that's a horse with only one sample. Okay. So what I'm saying is that what you are asking for is something which is really natural for us humans, but it's difficult for machine learning models. Okay. So, yeah, that's possible for some models. For instance, large language models are able to do something which is called future learning. So, they are good at that, better than these kind of models. But these kind of models, no way. If I train a model for cats and dogs, is only going to be able to distinguish cats and dogs. But if we want the model to distinguish also horses, we will need to get 100 samples of horses, train the model again, so that the model is going to be able to also distinguish horses. I don't know if that answers your question.
Uh, yes, I interpret or that I get is probably that the the excellent number for this model maybe could be 7.
No, the 7 is a number given by the problem that we are trying to solve.
Yes,
So
I
our problem is
yeah.
classified with 7 classes. So the problem is given, that doesn't depend on the model. It
Yes.
depends
What
on
I mean
on the problem that we are solving.
what I mean is probably that the number of the papers we have for this data set it fits the 7 for more. If I want more classes, I have to put it more data for the modeling.
for the new classes. That's right.
Yes, for the
You will
work,
need.
for the model works correctly.
Yes, 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 yes. Yeah, so but the point here is this number has to be 7, because if I put 8, let's make it. Let's see what happens. This is going to break probably
Yes,
somewhere.
and compare with the previous result.
But see, it doesn't break. Uh, oh, so yeah, we haven't
Yes.
run it yet, but we can try. But yeah, no, the 7 has to do with the fact that we are dealing with data that has 7 classes, and that's it. That's why. Okay. So if we have a different data set with more classes, yeah, we have to change this number. Okay.
Okay. Yes.
Okay. Okay. Ready?
Teacher, I got a question related to the Daniel question. If
Right.
we have another category that says, well, it doesn't fit in any of other categories, how can we train that?
If you have a new category, that means a new category for a new class, right?
A new class that doesn't gather any other of the 7 previous classes.
No, we have data. We have data for that class. For instance, here in this case, okay, let me see.
I
Here,
was thinking maybe
for
a data
instance,
set.
yeah, for instance, yeah,
Yeah, yeah.
here we have an additional one. Let's say
An
large,
additional
large,
class.
large language models. That is not here. Yeah,
No,
large
no,
language
an
models.
additional class that doesn't have to be related with any of their set. An additional class that says other, for example.
Other. Oh, other. Okay,
Exactly.
different to these ones.
Yeah.
Okay. Yeah, we will need to have samples for the other. We will need samples for other papers that belongs to other.
Okay. Okay.
Okay.
Okay. Thank you.
Okay. However, yeah, some of you that are here that are taking the machine learning class, yeah, actually, I can have like an additional class um, for when the model is not very sure about the decision. Okay. Without having samples for that. So yeah, that what you call other, it is possible. That's called a rejection class. When the model that the when the model says I'm not very sure, so I will not commit with any of these 7 classes, I will say other. Yeah, that's possible as well. Okay. But yeah. Yeah, I cannot go into details. I'll invite you to take the machine learning class for discussing that. But yeah, that's possible. Actually, yeah, that's possible without without having samples. Okay. Yeah, but I don't know if that was your original idea. Probably when you were thinking about the other class.
Yeah. Yeah. Exactly.
Oh, good. So, yeah, that's called rejection. And actually, yeah, that's something that we discussed in the first classes in Bayesian decision theory. The videos of the machine learning class are in my web page, so you can go there and check if you are interested. By the way, okay, okay. So let's go back here to this one, convolutional graph neural network. Okay, so yeah, so here basically what we are doing is we are creating the adjacency matrix. This is something which is called a sparse matrix with the source, with the target. This represent the links, okay? And this is what we are sending when we create an instance on my data set. We send the number of features, which is 14, here we have it. Yeah, the numbers of the size that is there. Yeah, for 14 something, okay? For 14,100, sorry, 1,400 something, okay? And we send also the adjacency matrix and then the labels, okay? And and that's it. Basically, with that, this creates the graph, and it's very simple, really, because Spectral already provides a class that creates a graph that you gives the number of features for the nodes, the adjacency metrics for the links, and the labels for the classification, and that's it. Okay. Okay. What else? Here there is something important. In machine learning, it's very important that you divide your data. You have to have data for training and data for evaluation. And actually, we divide the data in three groups: data for training, data for validation, and data for testing. What's validation? Validation is like a small data set that you use to adjust hyperparameters of your model. Okay, so validation is kind of training data, but you don't show it to your model during training. You use that to see how it performs when you change hyperparameters in your model. Okay, what's a hyperparameter? A hyperparameter is something, for instance, a neural network, like the number of neurons in a layer. That's a hyperparameter. That's something that you don't learn, but you can change to see if your model works better or not. The number of layers, the size of the embedding, the things that we were changing in the playground, things like that are hyperparameters. So you use validation. So we have to divide our data in train, validation, and test, but we have a problem. The problem is that we only had one graph with many nodes, and the nodes are connected. So how do I divide the graph? You can divide the graph. How? For instance, in this case, we are going to divide it like having three subgraphs. First, dividing the nodes. So there are some nodes that in this case are papers, some nodes for training, some nodes for validation, and some nodes for tests. Okay? And then it is important that the model knows that during training it cannot use the links, but in testing it can use the links. So that's because you have the edges. You only don't, you not only have the nodes, but you have the links, and you have to deal with that. Fortunately, uh, Spectral is very intelligent to do that, so we don't have to worry. So the way to tell Spectral that we have some nodes for training, some for validation, and some for test is use something which are called mask. So what we are doing here in this part of the code is building a mask. So a mask, what's a mask? Mask is basically a vector, the size of the number of nodes. Okay, so we have a train mask, a validation mask, and also a test mask. All of them are the same size, the size of the number of nodes. And they are going to have values which are 0 to indicate that that node doesn't belong to that particular mask. For instance, 0 in a train mask means that particular node is not going to use for train, or values which are different from 0, that means we will use that node for training. Okay, so those are the maths. So basically what we are doing here is building those maps, dividing the data in training, validation, and test, and telling Spectral to use those maps. Here, so that you can get an idea, here I'm printing some of the mask. So I print okay, a portion of the mask, because the mask is the size of the data set. So I'm printing a portion of the training mask, of the validation mask, and the test mask. So see, for instance, this sample is the sample 2000. It has a 1 for training, so that sample is going to be used for training, and it has a 0 for validation and a 0 for test. So that means that it's only going to be used for training. This sample, the sample, this will be the 2001, has a 1 for testing, a 0 for validation, and a 0 for train, and so on. So you can see that in every column there is only one. Okay, so those are the masks, and I use those masks to create something which are called loaders. See that in all the cases I use the same data set, but what I change is the mask. Okay, well, okay, these are some weights that are calculated based on the mass, but the weights are basically numbers that up to one and are only given to those elements that belongs in this case to training, in this case to test, and in this case to validation. Okay, so the loader for training, I have a loader for testing and a loader for validation, and it's the one that is going to load the data. Okay. Okay. What else we have here? No, that's all what we need. Really, we have to create the graph. We have to divide the data in training, validation, and test, specify the loaders, and that's all what I need. I create a GCN. GCN is Graph Convolutional Network. That's part of the models that are provided by Spectral. Okay. I have to specify the gain, the seven, the magical seven. Okay, which is the number of classes. So I have to tell a Spectral that we are going to have a graph convolutional network with seven classes. And I compile, remember that you have to compile a model in Keras. I have to specify the optimization, the algorithm that is going to do like the learning, and then the loss function, the one that is minimized during the learning, categorical cross entropy, and the metric that I'm going to calculate, which is accuracy. Okay, and what else? That's it. Let me see. Huh. Let me run this because I think there are some default parameters, and that's interesting to know what those parameters are. Okay. 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 Okay, so here we are training the model, which trains very fast. And but I think let me see here quickly because I think this GCN has some default parameter. Let me see if it shows something. Oh, but this is not going to show here. Ah, but this is going to end quickly. Okay. The array run. Okay. So let me see what parameter we have here. Just one moment. No, yeah, we can go to the documentation, but yeah, here just the important thing is, yeah, here we the only thing that we specify was the number of labels, and see the performance of the model. Here is already trained. See that here we specify the loader for training, and in validation we specify the loader for validation. Okay, and here, yeah, the model train. These are the curves, and the important thing is, yeah, here we get, yeah, a good performance. It seems. Let's see how it does in testing, and it gets 83%. So remember, for the baseline model, how much do we got? Let me see here. We got 74% for the graph convolutional neural network. We got 83%. So we improved 10 points. This is not a very complex model. We can do better for sure. But the state of the art is around 90%. So this is not bad at all. And you see that it trained very, very fast. Okay. This is the summary of our model. So yeah, it have a graph convolution. We can take a look let me see here in the documentation of a spectral what it say. Oh no, this is the paper. Uh, layers data. Let me see. Yeah. So the hold on a second. I just want to see this. Where is this? The network that we are using. Models, GCN. Where is the documentation for that? I just want to see. These are layers. Models, here they are. GCN, this is the one that we are using. Okay. And let me see. Yeah, these are the parameters. Okay. Yeah, we will need to go and check the documentation of this model to understand what it's doing. But here we can, for instance, the number of channels. This is similar to what you do with a convolution layer for images. So this really produces like many versions of the graph. So here is producing like 16 versions of the same graph. It uses activation which is relo, what else? So math, this is typical. Yeah, nothing is strange here, by the way. Okay. Yeah, and even if you want to see how it is implemented, you can go here to the source code. But yeah, that's going to be yeah. Here is because this is an open project and to understand better what is it doing. Okay. And that's it. Basically, that's what I wanted to show you to illustrate that in fact for these kind of problems using graph neural networks can have a lot of improvement. Okay, Daniel.
Thank you, Professor Fabio. Making a recap, what we have in this graph convolutional network. So is an operation after they have the graph divided in the three ways you show us in the page, in the web page.
Right. Yeah,
We have we have an operation with the convolution,
right.
uh, maintaining the nodes, and use the vector and the edges for universal.
That's right. That's right. Basically, what happens is that I really haven't checked the details of the graph convolutional neural network. By the way, this is something that I learned preparing this class for last semester because that's not something that I work on. And as you can see, this is really wide topic. So yeah, what happens in a convolutional in a graph convolutional neural network? Basically, what they do is a transformation of the network. But the thing is that if it is similar to the kind of transformation that you will make in a convolutional layer in a traditional convolutional neural network for images. What do you do? Basically, what you do is you create from an image, you create another image, but that new image is like a transformation of the original image that emphasizes some aspects. Okay, so what does it mean to transform an image? To change the information in the pixels. Okay, so when you apply the convolution, you say, okay, this convolution will have 10 channels. So that means that you generate like 10 versions of the image. Here is something analogous. You do a transformation, but that's a transformation at the level of, I'm not quite sure,
Where the
but
adjust,
I think it's vertices and the convolution are vertices and edges, basically. Okay, I'm not sure if it transforms. It makes a global transformation. My guess is that the global transformation there is like a global pooling at the end. Is my guess. So what you get is like different versions of the input graph, as many versions as channels. We checked, there was that there is a parameter that is called channels,
yes,
and it was 16, so it creates like 16 version of the neural network, and then it is able to integrate that information. When you apply several layers of that, it can integrate that information of those channels, and again do the same kind of operation. Okay, so is my guess. We will have to check the details, but that I haven't checked yet, but that's the idea. Okay.
thank you, Professor.
Okay, and any other question or comment? Everything clear? Okay, okay. So I think we are done. Professor Fernando, I don't know if there is something else for today's class.
Uh, from our side, maybe we can highlight some things regarding the new frontiers of data science, network science, sorry. But I don't know, do you guys have any additional comment or question regarding Professor's talk and the notebook that he just showed? Is it clear?
It seems so.
I guess so. Let me just
So yeah, I think we can go ahead.
okay, so we can, yeah, I can take over because I want to show my camera. Okay, so yeah, this is just an introduction, right? Like just a very brief, quick introduction to the topic. So there is a lot to be done, but I think Spectral is a very good tool, right, Professor? That they could like maybe use in the future.
Definitely, yeah. I think it's very easy to use. Works with TensorFlow, which is also easy to use, and with Keras. So yeah, I really suggest you to give it a try.
Okay, thank you, Professor. I think you don't need to stick to the rest of the session, and we can. And thank you so much, and we appreciate your presentation. Well,
Thank you very much.
okay,
Thank you very much for the invitation. Okay, bye
okay,
bye.
bye, Professor. Thank you so much. Okay, I just want to maybe just to, because we don't have much time, maybe just let me see. I have here the video of the section that we had last term or last year actually. So maybe we can go quickly on that because we don't have much time. Let me just share my screen here to say, and this is it. This tab. And yeah, just maybe highlight some things regarding some of these new frontiers of network science. Actually, this is last year's talk, but this is like just a video clip. I'm going to show a video clip from this lecture in deep learning class from MIT. MIT. So let me just start with. We don't have time to go over the whole video, but just maybe I'm just trying to make sure. Oh, the captions are already there. Sorry. Then I'll just play it from here on. Just a second while it loads. It's buffering. Be patient, please.
Okay, so let's focus on this first concept of how we can leverage more of our human domain knowledge to encode greater structure into deep learning algorithms. Turns out we've already seen examples of this in the course so far, particularly highlighted in CNNs used for spatial processing and visual data. As we saw, CNNs were introduced to be a highly efficient architecture for capturing spatial dependencies in data. And the core idea behind CNNs was this notion of convolution, how it would relate spatially similar and adjacent portions of an input image to each other through this efficient convolution operation. And we saw that convolution was able to be effective at extracting local features from visual data, and then using this local feature extraction to then enable downstream predictive tasks like classification, object detection, and so forth. What about now, instead of images, if we consider more irregular data structures that can be encoded in different ways beyond 2D grids of pixels? Graphs are a particularly powerful way of encoding structural information. And it can be, in many cases, that the notion of a graph or a network is very important to the problem that we may be considering. Graphs as a structure and as an example for representing data are really all around us across many different applications, ranging from social networks, defining how we are all connected to each other, to state machines that describe how a process can transition from one state to another, to metrics and models of human mobility, urban transport, to chemical molecules and biological networks. And the motivation across all these examples is that so many instances of real-world data fall into naturally this idea of a network or graph structure, but that this structure cannot be readily incorporated or captured by standard data encodings or geometries. And so we're going to talk a little bit about graphs as a structure and how we can try to represent this information encoded in a graph to build neural networks that are capable of handling these data types. To see how we can do this and approach this problem, let's go back for a moment to the CNN. In CNNs, we saw that we have this rectangular 2D kernel, and what it effectively does is it slides across the image, paying attention and picking up to features that exist across this 2D grid. And all this the function is doing is that element-wise multiplication that defines the convolution operation. And intuitively, we can think about convolution as this visualization of sliding this kernel iteratively, patch by patch, across the image, continuing on to try to pick up on informative features that are captured in this 2D pixel space. This core idea of convolution and sliding this feature extraction filter is at the heart of now how we can extend this idea to graph-based data. This motivates a very recent type of neural network architecture called graph convolutional networks, where the idea is very similar to standard CNNs. We have some type of weight kernel, and all it is a matrix defined by neural network weights, as before. And now, rather than sliding that kernel across a 2D grid of pixels, the kernel goes around to different parts of the graph, defined by particular nodes, and it looks at what the neighbors of that node is, how it's connected to adjacent nodes. And the kernel is used to extract features from that local neighborhood within the graph to then capture the relevant information within the structure. So we can visualize this concretely here, where now instead of seeing the 2D kernel looking at a particular patch of an image, what I'm highlighting is how the kernel is paying attention to a node and its local neighbors. And effectively, the graph convolution operation, what it's doing is picking up on the local connectivity of a particular node and learning weights that are associated with those edges defining that local connectivity. The kernel is just then applied iteratively to each node in the graph, trying to extract information about the local connectivity, such that we can go around and around, and at the end, start to bring all this information together in aggregation to then encode and update the weights according to what the local observations were. The key idea is very, very similar to the standard convolution operation, where this weight kernel, all it's doing is a feature extraction procedure that's now defined by nodes and edges in this graph rather than a 2D grid of pixels in an image. This idea of graph encoding and graph convolution is very exciting and very powerful in terms of now how we can extend this to real-world settings that are defined by data sets that naturally lend themselves to this graph-like structure.
Before we continue with the examples, so is it clear for you guys, like what and this is one of the basic, let's say, graph neural networks, the convolutional neural networks, and you can consider it as a feature structure, of graphs. So because what the neural network is doing is actually like extracting let's say the local or the essential features of the graph and getting a new representation inside the neural network. Is that clear for everyone? And that's what in the case of convolutional neural networks is for images, and I think somebody asked something about that in the session today. That what you are doing is actually extracting some features from the image. The typical example is about images, but I just wanted to highlight, Professor, he went fast, and he didn't go over that. And there was no time to go over there, but the definition of convolutional is a mathematical definition for any type of signal. It could be one-dimensional, two-dimensional, or three-dimensional, and so on. It's just an integral or two double integral and so on. So and that's why I invite you to please go over the interactive page that I shared with you guys, and you can see the effect of the convolutions in 2D and 3D in that particular example, in those particular examples that you can see there. So you do the same thing. You just go traverse the graph, and you go around the graph, extracting the local features of the graph by looking at the particular node and its neighbors. Is that clear for everyone? And then you can do whatever you want with that representation inside the neural network. Okay. Okay, let's continue. Just a few more minutes here with her, with this lady.
So to highlight some of those applications across a variety of domains, the first example I'd like to draw attention to is in the chemical and biological sciences, where now if we think about the structure of a molecule, right, it's defined by atoms, and those atoms are individually connected to each other according to molecular bonds. And it turns out that we can design graph neural networks that can effectively build representations of molecules in the same operation of this graph convolution to build up an informative representation of chemical structures. This very same idea of graph convolution was recently applied to the problem of drug discovery. And in fact, out of work here at MIT, it turned out that we can define graph neural network architectures that can look at data of small molecule drugs and then look at new data sets to try to predict and discover new therapeutic compounds that have potent activity, such as killing bacteria and functioning as antibiotics. Beyond this example, another recent application of graph neural networks has been in traffic prediction, where the goal is to look at streets and intersections as nodes and edges defined by a graph and apply a graph neural network to that structure and to patterns of mobility to learn to predict what resulting traffic patterns could be. And indeed, in work from Google and DeepMind, this same modeling approach was able to result in significant improvements in the prediction of ETA, estimated time of arrival in Google Maps. So when you're looking at Google Maps on your phone and predicting when you're going to arrive at some location, what it's doing on the back end is applying this graph neural network architecture to look at data of traffic and make more informative predictions about how those patterns are changing over time. A final and another recent example was in forecasting the spread of COVID-19, where again, building off of this same idea of mobility patterns and contacts, graph neural networks were employed to look at not only spatial distributions of COVID spread, but also incorporate a temporal dimension so that researchers could effectively forecast what were the most likely areas to be affected by COVID-19 and what timescales those effects were likely to occur on. So hopefully this highlights this idea of how simple ideas about data structure can then be translated into new neural network architectures that are specifically designed for particular problems in relevant application areas. And this,
Yeah, I think I also would like to maybe go back to at the beginning of this video. There's some things that in which Professor Alfonso highlights a few things I would like to show here regarding the structure. Here we go. See, this is for somewhere around here.
We want to talk with you, with the students about network science, about the course a little bit. I'm going to talk about 10 minutes initially. Then I'm going to put a video, and then we can talk, okay? Let me share the screen. Tell me if you are okay. Tell me if you are seeing my screen.
Yes, we are, teacher.
Okay, thank you. You are seeing a PowerPoint presentation? Okay. Yes. I don't know if you recognize this building, these trees. Someone could tell me?
I could read MIT, but
okay.
I didn't
You will hear at the left MIT. Okay, okay. That's correct. Here are networks. This is the building, an important building in MIT, Massachusetts Institute of Technology. This semester, they began a course. A course they have been given about, I guess, 10 years. Or I don't know,
7 years. Introduction to deep learning. This is the hot topic now. Chat GPT, generative models, training models, but also networks and graphs. Okay. What is the name of the course? Is MIT 6S191. Okay. This course is open. It's in open courseware, a website of MIT that for 15 or nearly 20 years is full of open courses, okay, of all types. This is Introduction to Deep Learning. Here, 200 2023 edition. Okay, they are now. I guess now they are students are receiving this course, and maybe they are doing projects like our projects in this course. And here, it's a network. Okay. Let me go to the next slide. Okay. Let me. This is lecture 7. This is lecture 7 of the course. Limitations and new frontiers. New frontiers in deep learning. Okay. Limitations and new frontiers in deep learning. It's a young teacher, Ava Amini. In this lecture, she talks about neural network limitations. And one of the limitations he mentions is difficult to encode structure and prior knowledge during learning. Okay. And then he talks about this topic, encoding structure into deep learning. What is the translation of this to our course? Graph neural networks. Okay. This topic that Dr. Fabio Gonzalez talked about. Okay. When she talks about encoding structures, he began with a classic
Yeah, I would like maybe to just to highlight and maybe allow Professor in the last couple of minutes to stress a little bit about this, like because, and that's what happened, in the past, since we have like complex structures such as graphs, what we always did, and other type of, structures like that one, we always did was making them simple, reduce them, to a simple representation. So what we have done now with this, and we have seen in the class, is just work with the graph directly with the natural structure of the graph, or in this case, like what we saw with Professor Fabio's talk, is that we actually, though we use some vector representation, we still keep the main aspects or the essential aspects or generalities of or details of the graphs themselves. Professor, I don't know if you wanna maybe just close to wrap up the session, talk a little bit about this encoding the structure for example, in this case, in the graph neural network. Professor Alfonso.
Thank you. Thank you, Luis Fernando. We have been dealing all in this course about network science, and in this last session, these last 2 sessions, we want to show you the the, the future of network science, that I guess is also the future of machine learning. They are being joined, by the graph neural networks. And I think this is a very important topic for the future. So we want to show you in these last sessions this topic because it's very important. We know that this topic is not to be in the I guess in the project you're going to present. You're going to present your projects based on classical network science and also on new ways of seeing network science that we have found in your projects. So I guess this is the end of the course. I hope that you have get motivated to this important theme, and and we wish you very good luck in next week in your presentations. I don't know, Luis Fernando, if you have any more to say.
Yes, maybe encourage you guys to go deeper. And even Professor said that if you want to go into more details about machine learning, just to encourage you to take some of the machine learning class. Professor, I'm not so sure. Can anybody tell me because I get confused? Is he teaching the machine learning class this term or is it next term? I think it's this term. Is anybody in that class by chance? Any of the participants here in the class? Manuel? Manuel? Can hear you. Yes. You are taking the class, his class this term? Is that what you're saying, Manuel?
Yes, teacher. I am seeing the machine learning class with Professor Fabio.
Okay, good. And yeah, but if you haven't taken it, maybe you will have to wait, I guess, one more year. So I guess he offers it like every year in the first term of the year. And unless something extraordinary happens, well, we don't even know when we're going to start the next term in our university. But I'm planning to teach the neural networks class again. So we go into some of the details about deep learning, and we have a small part module there on graph neural networks. And I was thinking, Professor, I don't know, maybe I think it's worth, in the future, maybe next year or so, to have just a whole class on graph neural networks, right, Professor? Don't you think?
Yes, I guess we have to plan that because graph machine learning is now a big topic,
A hard
and
topic.
it deserves a complete course. A complete course. What Fabio said today and what we took the last session is it's only a tiny part of a big topic that is real now. There are real applications, real in drug discovery, for example, there are a lot of new discoveries using this topic.
Yes, actually, one of my students, we didn't have time, but I wanted to invite him to this class, but fortunately we didn't have time. And just in case anybody is interested, Juan Guillermo is working on this topic. Actually, it's the same idea about what Professor was saying about drug discovery, or what Professor Amini was saying, the MIT professor, regarding this drug discovery to develop antibiotics and that. But in our case, it's just like the basics of like developing vaccines, the RNA vaccines. But anyways, let me see. Somebody said something, and I guess we kept you. This is the reason the things that Professor is here in class and this point that you share with us where the center is covered. Oh, Sebastian. Okay. Yeah, I just shared. No. The one that I shared was the one that I shared just now on the chat. Just to clarify, was the one that I was just showing now, but because there are some other videos that may be of interest for you guys. But of course, we are going to share the last today's session on Google Classroom regarding the details about like this graph neural networks and that particular application. But this is just a general overview and basic introduction to graph neural networks. Okay, Sebastian. Okay. So,
Okay, Professor, thank you.
okay, thank you. So I'll stop recording, and I guess we'll see you next